Okay, hello everyone. Welcome to recitation number 8. It's the last one, so congrats on making it this far. Technically, it might be the last time we talk since if your reading period starts next week, like if today is the last day of classes, technically you don't need to attend Monday when I review your exercises. I'm gonna do that either way. Like if next week is the reading period or not, I'll do at the same time. Is it 12? No, we do it at 5. I'll do the same time where at 5 p.m. Monday we'll go over the exercises. Your exam is when? On Tuesday? Like the final exam in this course. Has it been scheduled yet? Well, as long as it's after Monday, I'll still do that at the same time. You can either attend or not, and I'll have it uploaded on the playlist. Anywho, so make sure if you have any questions, make sure they're ready. Okay, so your exam is on Wednesday. Okay, that's good. So it's on Wednesday. I'll be there Monday reviewing the exercises. If you want to be there as well, great. And if you have any questions, like that's the time. Okay, like really the last time or chance. We'll still be there Tuesday, even Wednesday morning on the forum, but like this talking, Monday's your last chance. Okay, so today is about, first of all, recursion. Then we'll reach counting at the end. Starting with recursion, won't dive too much in the explanation. You already know functions. Recursion is when you call the function within itself. What do I mean? Let's just see an example. Write an algorithm to find the sum of digits of a number using recursion. Okay, so sum of digits using a recursion. So if you have this number 1, 2, 3, 4, using recursion, or for example, just what's the problem asking? You want the sum of the digits themselves. So the answer here would be 1 plus 2 plus 3 plus 4, whatever that is. So maybe 10. Now, how can we actually solve that? Let's try to solve it in the normal function. How would that happen? Well, function, procedure, method, whatever you want to call it. It's going to take a list of, it's just going to take the number. So let's say number is n. Well, I want to take the integer part of each one and sum them. How can I get that? Well, you're going to use two things, either division or modulo. You're going to need both of those. For example, 1, 2, 3, 4. If you modulo it with 10, you'll get 4. If you divide it by 10, you'll get 1, 2, 3. Without the decimal point, like we're talking if you take the floor, like just the integer part without the decimal part. So that's what you want to do. First, you'll modulo the number, so you can get the last integer part. Then you'll divide by 10. You'll keep doing that until your number becomes 0. So again, I have 1, 2, 3, 4. If I modulo it the first time, I'll get 4. 4. Modulo it by 10. Then I divide by 10, I get 1, 2, 3. That's like step 1. Step 2, 1, 2, 3, modulo 4, get 3, divide by 10, get 1, 2. So on until number's over, and all the while, of course, you're summing these digits. So how can I do it? Well, I have my number n, it's an integer. Start with, hey, sum is 0. While n is bigger than 0. Like we'll keep doing this while n is something positive inside the while loop. So these braces just means here's my while loop starts. Here it ends. Instead of braces, you can write, for example, end while, if you're more comfortable with that. So what do I want to do? First, add to the sum the division, the modulo. So n modulo 10. That means we're taking the integer, the last digit, and we're adding it to sum. So with the example 1, 2, 3, 4, right now in sum, I have 4. After that, with n, what do I want to do? N equals n divided by 10. That's it. Take a second to look at it. Okay, so that's an iterative way of doing it. What about a recursive way? Well, since we have a loop here, it's kind of hinting you can turn it into a recursive format. So how can we do that? Let's just add a slide here. Okay, so iterative, let's now do a recursive form. So we need to name the function something. Let's call it function, or let's say something that makes sense, recursive sum. Again, it's going to take some integer n. With recursion, you have to think of usually two things. Your base case, or like your end case, like when do you stop? Because recursion, it's going to keep calling itself until you hit something that's going to make it stop. So in our case, when did we stop with the for loop? When n reaches 0. Okay, so for example, if I want to continue with 12 modulo 10, I get 2. Divide by 10, that's 1. Last step, 1 modulo 10 is 1. Divide 1 by 10, I get 0. There's no more need to keep going here. That's it, it's 0. I just have to sum the modulo parts. So I sum, where are you? Here I am. 4, 3, 2, and 1. All that's happening in this step. So my base case is going to be if n is, let's say it's equals 0, then stop. Don't do anything. Like return 0. We'll see what we mean by return in a moment. It's just like, hey, if your number n is 0, it's done. Should we check in our pseudocode the step where we check? Oh, okay, I don't understand your question, but if you said I mentioned it, then great. So if n is 0, stop. Like if you're given a number which is n and it's 0, what's the sum of the digits there? It's just 0, which is why we return 0. What about the recursive step? Okay, so return n over n modulo 10 plus recursive sum of n over 10. So that's it. So you're saying if n is less than or equal to 1, you can return n. Return n plus recursive sum of n minus 1. Not exactly. In what you're saying, so some Reem, you're saying you want to do this. You want to return n plus recursive sum of n minus 1. Remember, the question is saying you want to count the digits. So 1, 2, 3, 4. Like this is 1,234 or 533. The answer to 533 is going to be 5 plus 3 plus 3. And what you're saying here, it's going to return 533 plus recursive sum minus 1. So 532 plus 531 all the way down. That's not what we want. Yeah. No, that doesn't even have to do with Fibonacci sequence. We simply want to do this. So let's see why it works or how it works. Again, we started with recursive sum 1, 2, 3, 4. So is this number equal to 0? No. So we don't do this step. We reach this step. What is it saying? Return n modulo 10 plus this. So this is going to return, the answer to this is going to be n modulo 10, which is 4, plus recursive sum of dividing by 10, which is 1, 2, 3. So this is a variable we don't have the answer for it yet. And this is where the recursion is happening. So right now, the answer for 1, 2, 3, 4 can't happen before I get the answer for 1, 2, 3. So we keep going. 1, 2, 3. Is it equal to 0? No. So I go to the recursive step. The answer to recursive sum of 123 is going to be 123 modulo 10, which is 3, plus recursive sum of 12, because I'm dividing by 10. And still not 0, I keep going. Modulo 10, I get 2, plus recursive sum of 1. Is 1 equal to 0? Still no. 1 modulo 10 is 1 plus recursive sum of 0. Each function behind me is still waiting for an answer. It's not done yet. It's still waiting, like it entered a queue. But the last call, recursive sum 0, well, hey, n is equal to 0, so I return 0. The answer to this is just 0. Now we backtrack. So what's the recursive sum 1? It's just 1 plus 0, so it's 1. What's recursive sum 12? 2 plus 1, so it's 3. What's recursive sum 1, 2, 3? It's 3 plus 3, 6. And finally, what's the recursive sum of 1, 2, 3, 4, my original call? 4 plus 6, 10. That's how it goes with recursion, usually. Like that's an example. We started so many colors. We started here with our original call. Like I wanted the recursive sum of 1,234. But in order to get that, it had to get broken down into these many steps, into my recursive step, until finally I reached my base case. Once you reach your base case, you can, now I can backtrack all the way up and get what I want. Okay. If you have any questions on this, if you have, let me know. Because the next question is your turn. Write an algorithm to check whether a given string is a palindrome or not. What's a palindrome? It's just a word or a bunch of characters. If you reverse them, they're going to stay the same. So for example, madam is a palindrome. If you read it both like this or like this, it's the same. Ma'am is a palindrome as well. Dest is not a palindrome. DESD is also not a palindrome. It's different. How do we check if a word is a palindrome? Well, we'll check the first character, the last one, they're the same. Then they make the arrows come closer. They're the same. Make the arrows come closer. Same. That's it. This kind of feels like a two-pointer idea that we discussed last time, right? So I'll do it real quick in an iterative way, and you guys have to try to do it recursively. So imagine you have a function. It takes the letters, like we're gonna break it down into characters so it's easier to work with. So C1, C2, Cn, such that each C is just like one character. So that's how we'll break it down, the word. I'll make start equal 1, end equals n. Now I'm checking. While start is less than or equal to end. This is my condition. I'll explain it in a second why we did that. But what am I testing for? I'm testing, hey, if if C start equals C end, that's something good. I want to continue. So what I'm going to do is, if they're different, I'll break. Otherwise, I'll just say, hey, start increment by 1. So plus plus, it just adds 1. And end minus minus. Let's see what I wrote here. Start is less than or equal to end. So bear with me. So it starts with 1 and it starts with end. So the first, again, I'm going to write here, madam. Here I have start. Here I have end. Does C start equal C end? Does M equal M? Yes. So I don't enter the if statement. What I do is start plus plus and minus minus. So now I am like moving my arrows. S is here, E is here. Are they equal? Yes, I don't enter the if statement. Plus plus minus minus. Same character, so they're definitely equal. Plus plus minus minus. They flip. So now end is here and start is here. So like they crossed over. That's when my condition breaks. Start is no longer less than or equal to end. This is like an indication that I went over all the characters and they're all equal. So what you do is, after the loop is over, you can check if start is strictly greater than end, like they crossed over, that means it's a palindrome. So you can print palindrome or return true. Otherwise else, it's not a palindrome. Like for example, if I'm doing DESD, start, end, they're equal, great. Plus plus for the start, minus minus for the end. E does not equal S. So I enter this loop statement and I break. When I'm testing what does start and end, they're like start is not greater than end. That means they never crossed over. So I stopped at a certain point, which means it doesn't work. So there's that. That's how you do it iteratively. Try to do it recursively. If you have any questions, let me know. Like if you feel this might be too difficult, if you'd rather I solve it recursively, okay, but at least take a minute or two to try think of, like for example, what would your base case be? When would you stop? And we should mention that, so before we were using, with the return here, we were using numbers. So I was returning 0, I was returning 3, and so on. Here, recursively, at a certain point, you want to return true or false. So in your base case, for example, you'd return true. Otherwise, you'd return false. Like no, like yes, it is a palindrome. No, it's not a palindrome. So take a couple of minutes and we'll see what you guys get. At least try to think of a base case, like when should I stop? And what could my recursive step be? And another hint, your function, like if you want to say recursive palindrome, it's going to take C1, Cn. It's going to take start and end. When you recurse, you want to increase this, you want to decrease this. Reem, I'm not sure what does this state. Okay, so if the statement that I just sent you, if this just simply reverses the last string, like if you're just the first string, you're comparing it with the reverse of the second string, that's kind of not allowed. So that's like what we meant when you, if you want to use Python, okay, sure, but you have to write all the steps. Okay, great. So this does reverse your array. Like it's like this is a for reversing an array, that's like a for loop that you're skipping. So you can either actually with your hand reverse the array and then it's fine, or you have to come up with another method. So like you need to write the details of what you mean. Like if you're using a shortcut to reverse or a shortcut to sort, you need to write that. But in general, the idea would work. Sure, that's also an idea. No, no need for it to be complicated. Just assume it's all lowercase and just, yeah, lowercase. You can assume it's all letters if it's easier as well. Or should we include? Well, you can ask then in the exam if the instructions aren't clear enough or what you should do, you can ask that moment. Okay. One more minute and I'll show you the solution. We got a lot to solve today. So again, just pseudocode, just what could your base case be? What could your inductive step or recursive step be? Okay, let's do this. So do we have to write it always iteratively and recursively, or that would be specified? That should definitely be specified. The reason here I'm doing it iteratively and then recursively, so that you can at least understand how it works, and you just have to translate it into recursion. But definitely it should be specified so you don't waste time. So here, how can I take from this iterative method, how can I take the base case, or when do I stop? Well, it's sort of this. Like, when did I return an answer here? So like say later, let's say you're checking your characters. When do you stop? Well, when start has crossed over end. When that happens, you definitely know that you're done, so you can, hey, simply return true. That's it. Otherwise, check the current characters you're at, which are again start and end. So if C start does not equal C end, return false. This isn't really a base case. It's true that we're returning something. So like it's stopping the function, but this isn't a base case. This is like it's part of your code. You're just checking, okay, should I stop now or not? This is your base case because that's it. Start and end have crossed. If you keep comparing, you'll keep going on forever. Here, no, we're just checking, hey, at this step, are they equal or not? If not, stop. Return false. This is not a palindrome. Otherwise, you'll return recursive palindrome of the same string, start +1 and -1. That's it. But of course, let's see why it's true. So let's say, madam. So when you first call this function, you're going to give it recursive underscore palindrome, madam, then start is 1, end is 5. Okay, because it's 5 characters. Well, first thing you ask yourself, is 1 greater than 5? So is start greater than end? No, 1 is not greater than 5, so you don't do this. Is the current characters you're pointing at, are they different? No. Again, we don't care about case sensitivity. They're not different, so you don't return false. Finally, you go to the recursive step. So the answer for this is going to be the same as this, but with the start and ending moving. So now we're pointing to the A's. 2 is not greater than 4. They're not different, the two A's. So again, you go to the recursion, same word, 3 and 3. Well, start is technically not greater than end because 3 is not strictly greater than 3. So you're gonna go through the whole thing again, or we can add here or equal. Because once start equals end, like it's definitely also gonna be a palindrome. Because like your two characters are gonna, your two pointers are gonna be pointing at the same character. So like they're definitely gonna be equal, and it's just like an extra step that they cross. The reason we have the or equal is because if you're working with MAM, like if it's even, the number of characters, it's even, it's important to have the greater than, because you start like this, M and M, then A and A, then they flip. This A, start and. That's why it's important to have greater than. We can write while start is less than end instead of the statement. On the other side, you mean, in the iterative? Yeah. You don't need the or equal here either. But then here you'd have to say or equal if start is greater than or equal. So like depends. If you want to remove the equal here, you have to add it here. Why? These are the little details. You can focus on them and figure it out. Okay, finally here, if we add the or equal, 3 is greater than or equal to 3. Again, we recursed 3 2 times and we reached 3, 3. They're greater than or equal. So you stop and you return true. So the answer for this is true. But the answer of the above it is the same. And the above it is the same. You're done. In the example of MAM, you'll stop at start is going to be 3 and end is going to be 2. So like you start 1, 4, then 2, 3, then 3, 2. Here they flipped. Okay, so that's how we do that. Any questions so far? Okay. I did have one more question on recursion. I'm going to do it because this is a very nice question. I'm going to do it, and it has to do with some of the questions later. Okay. Hopefully by 6, I'll finish the recursion stuff. If you need to leave, you can leave then, and then I'll do another part that has to do with the counting. You can revise later. If you can stick by for the whole time, then great. Okay. So any questions before we move on? Great. Assume you are standing on the origin of a 2D Cartesian grid. So you have this thing. We need to reach a point NM. But we are only allowed to move up or to the right. So let's say this red box is my destination, and I start from here. I can only move one unit and either up or to the right. So I can either go like this or like this. We want to make an algorithm recursive. This time we're gonna do it just recursively, no iteratively, because it actually might be easier to think of it recursively here. But anywho, we can just move up or to the right, and we have to count all the possible ways that we do that. So for example, if I go up, so up here, then up here, then I go to the right 1, 2, 3, 4 times, that's one way of doing it. Or I could go to the right 4 times and then up twice. That's another way of doing it. Or upright, whatever gets me there. Like basically it's going to be all the combinations between these. So how can I do that? Well, the thing is, if you move up or you move right, that's going to be a unique road that you're not going to take. So let's say this point here. I'm going to color this box with purple. I can either reach it using up, then right, or right, then up. The purple box doesn't care how I got there. So once you reach there, then all you care about, hey, I can either move up or to the right. So what are my base cases? I know I have this here. You can try to solve it again on your own time, but I'm gonna do it now. What are my base cases? Well, all I have right now is, let's say I have N and M, like my destinations, and IJ, my current location. So NM is the XY I want to reach. IJ is the XY where I am at. What are my base cases? Well, if I reach my destination, then that should say I'm done, right? If I reach where I want to reach, I can return 0. Like I'm done. Otherwise, I can either move to the right or to the left or up. When am I able to do both? Like let's say I go up here. I can't move to up anymore because if I do, I skip my destination and I can no longer come down. So if n equals I, that means I can only now go right. So return 1 plus, I called it function, so I'll just say function of nm is going to stay the same, I is going to stay the same, j plus 1. This is just saying I moved once to the right. Oh, wait a second. Actually, my bad here. I think it should be once you reach your destination, you return 1. Like, oh, I reached my destination, so that's one way of doing it. Okay? So if n equals I can only go to the right. My other case is if m equals j, that means I can only go upwards. So that's saying like you kept going to the right, and now you can go up. So return function and I plus 1 j. Okay, good enough. But I still have one condition, which is what if this is false and this is false? That means like I'm kind of, for example, in my start position. It's possible for me to go either up or go to the right. So I can simply return function. I wish I called it something better. And I plus 1 j plus, because remember, you can only make one move. You can't make two moves at the same time. Function n I j plus 1. So the last step is saying, hey, if I can move either up or to the right, then I'll do both. Then I'll like do both scenarios. The scenario, I'm moving upwards, let's say, and the other one, I'm moving to the right. Okay, I got lost which if it's up or right, but it's like either this or this. One of them is going on. Eventually, for each of these functions that reaches this base case, you're gonna count 1. Let's see if it works. But before we actually see if it works, again, what I'm saying is my base case, if I reach my destination, count 1. I reached it. This is saying if I can only go, okay, so I is my x. Okay, so I guess this is saying I can only go upwards. Because if we're assuming that I is my x, it means I can no longer move to the right. So if this is x and this is y. This is saying I can only go to the right. So my j, my y is to the max. Otherwise, hey, go once up, go once right. Whew. But this way is only taking one path. No, this should be taking care of all possible cases. Let's see an example. Okay, great. I pressed discard, so the whole thing went away, but that's fine. We all remember what I wrote, I'm pretty sure. So I want to make it easy. So let's say I want to reach this spot. I want to start from here. So I want to check all the possible ways. So my ij is currently 0, 0. My nm is, let's say, 1, 2, 1, 2, 2, 2. Nm. And this is my ij. So I started with function. I'm just going to write I and j since n and m is always going to be the same. So I started with 0, 0. Is my base case correct? Like, does 0, 0 equal to 2? No, so I don't return 1 just yet. Is one of them equal to 2? No. So it's not like I can only move one way. So I reached the case where, hey, they're both less than, so I can go either up or down or right. So for example, F01 and F10. Now for this one, it's gonna break down to F02 or F11. Same for here, F11 and F20. So these are like the positions where I am currently at. Now it's true that this is f11 and this is f11. Like this is saying that they both reached this. First one is saying, hey, go up, and then go to the right. So this, then this. Whereas this is saying, hey, first go to the right, and then go up. So it's true I reached the same point, but I took a different road. So there are different roads. Now what about this guy? 2 is, it's my maximum. Okay, so this is saying go up twice. So I'm here. I can't go up anymore, so now I can only go to the right. So that's saying now I have to go F1, 2, and after that I go F2, 2. Yes, 2, 2 does equal 2, 2, so this is gonna return 1. So that's like one road where I reached my destination. No, this is not, this can still break down into either F1, 2 or F2, 1. After that, F2, 2 and 2, 2 again. So again, returns 1, returns 1. So in the paths where I'm starting by going up first, there's 3 possible paths. I assume it's gonna be the same for below. So it should be 6 possible paths. Is that true? Let's try to do it. So, so I can either go, so this is one way, or second way, 3, 4. Confused. So, yeah, it's 6 because I missed another path. So you can go like this. Okay, or like this, that's 2 paths. Okay. Or I can keep going up and then to the right. Yeah, I think it's 6. If you try to draw them out in a way better way than what I'm doing, they're gonna be 6. Okay. So yeah, I wish I still had the code, but it's gone. But that's good, because you can try to do it on your own now. Again, you just had to think of all the cases. I'm gonna repeat it once, but really, if you didn't completely get it, that's more than okay, because you get the opportunity to solve it your own. Base case is when you reach the destination. So your I is j is gonna be your current position. Once that equals n and m, that means you're done. You reached where you want to reach. Otherwise, you have to think, is it possible to go up or right? If that's the case, then you're doing this. Like you're breaking down. You want the sum of both of these. You can either go to the right or up. Same here, either right or up. Otherwise, if you can only go right or up, you're doing this. Like it no longer diverges. But where did we save the number of times where we took another pass to reach Exactly, it's in the summation. So for example, you see how this is 1, this is 1, and this is 1? Well, where's the end? Okay, I'm gonna go backwards now. So we reached the end of the recursion, now I'm gonna go backwards. So the answer for this f is 1, this f is 1, this f is 1. Since here we diverged, in our code we wrote summation. So this f is going to be 2. This one is going to be 1. Summation, this f is going to be 3. It's going backwards. Since it's symmetrical, and this example is symmetrical, the one below us is also going to be 3. You can try out the cases though. Finally, sum, it gets 6. Okay, so where did we save the number? Same thing as the example 1, 2, 3, 4. Like I'm saying the answer to this function is the sum of both of these functions. So what do? I go find out what the value of these functions are. But they themselves are dependent on other functions, and so on. So I have to keep going down until I reach my base case. And the only base case I have here is this. If I reach my destination, I just return 1. It's like I'm counting. This road is 1. Okay? It's a very nice question. It's a little difficult, I won't say no, but I highly recommend you try to solve it on your own. If you have any problems with it, you can use the forums and let me know. Oof. Otherwise, it's really time to move on to the next question. Okay. So use master theorem to, okay, so I still have 2 ideas, one that has to do with master's theorem. The other is sort of recurrence relation. I'll do both of these and we're kind of done with the whole recursive function idea. Then I'm gonna do probably another maybe 45 minutes or half an hour, something like that, on counting. If you need to leave at any point, I understand, but try to revise them when you can. If you have any questions on anything we've talked about so far, let me know. Otherwise, master's theorem. This is really one of those exercises where it's 3 points. So what's master's theorem? You have a formula in this format. If you have these conditions satisfied, then depending on the relation of these values, you choose, like you just fill in the blanks. So for example, I'm going to have the formula right here so we don't lose it. For part 1, so what do you have? This is A, this is B, you have C is 1, and this is D. So if you just look at the values, you're going to get A is 2, B is 2, C, D is 2, and definitely C is 1. So your conditions are satisfied. All you have to do is now see what's the relation between A and B and D. In this case, it's this. A is strictly less than P power D. Why? 2 is strictly less than 2 power 2, which is 4, obviously. Since this is the case, that means your answer is going to be this guy. So it belongs to n power d, which is n squared. And it's kind of obvious. Don't want to say obvious, but it kind of hints when you have this O of n squared. So what is this actually saying? It's saying like your original program, it's let's say it's n elements. It's breaking down into 2 n over 2 elements, and it has a complexity of n squared. Sort of like that. So these themselves keep going. Oof. Try to do part 2 and part 3 right away. Like, seriously, just fill in the blanks before we continue. So these are very easy, just easy, 3 points if they come in the exam. Number 2 shows that d equals 0 exactly, and power 0 is 1. So you have a is 1, b is 2, d is 0. The relation is this. So you just plug in the values. Same thing for the last one. Plug in the values and you're done. Okay. So that's that. If you, again, you can still practice them on your own when you do. Change of plans. The electricity went off here and I don't know how long the UPS is gonna last. So we're gonna do this. We have one other exercise in this. We're gonna do it. We'll stop and then I'll see when I can do the counting. So it's log n. Yeah, that's what you got. It's log base 2n. Exactly. It's important the base. So the relation, it tells you it's base b. For example, this is actually this one. Okay, here it doesn't specify the base, but in the third one it does. I don't know if this is a spelling mistake or that's the law. Because when it doesn't usually, okay, it might be a mistake because here we do have it. Try to make sure about these values, how they should be. So write the recurrence relation describing blah, blah, blah. Okay, bear with me. So we have an algorithm. You have a very similar exercise in your assignment, and you want to find out what the relation is. So we want to write it something similar to what we have here. So let's actually understand what the function is. Max, min, the list, key, and index. So this function is trying to return for you two values, the maximum and the minimum in this list. It's saying if n is 2 and a1 is bigger than a2, return a1, a2. Otherwise, return a2, a1. So this is the max. This is the min. Max, min. Otherwise, if they're equal, you don't care, just return the same values. That's the base case, right? If you're writing something recursive and you have a list, your base case would be, hey, if I only have two elements, then one of them has to be the max, the other has to be the minimum. Now we go to the recursive step. They break down the list into 4 parts, S1, S2, S3, S4. So like we had n elements, now each list is going to have roughly n over 4 elements. Then what? We are recursively calling the function for each one of these lists. So remember, your original function, it has a list, and you're getting the max and the min using this magic. Now you broke it down into 4 lists, and you're recursively calling for each list. So what is this saying? Like the complexity of the current method, it's getting broken down into 4 n over 4s, right? Because these themselves are gonna recall and do all of this stuff, but for a quarter of the elements. So it's 4 times n over 4. And then we want to add to it, what else is it doing? Everything else that it's doing can be considered O of 1. Why? Well, this is just testing if statements. And here, it's true that we're doing the recursion again, but it's only for a specified amount. So at the end, after you have the couples max min, max min, max min, max min, on that, you're doing the recursive call again, as you can see here. But the size of this array is 4, and this array is 4. So in the first one, you're like getting the max of the maximums. The second, you're getting the min of the minimums. Because we have 4 maximums, 4 minimums, because we broke down the function and the list into 4 parts. But what I'm trying to say is you can consider this as O of 1 because the size of the array is something constant and it's small. It's just 4. it's roughly the whole things might be like O of 10 or O of 20, but we assume this is just O of 1. So what's the complexity of this thing? Well, we can go back here and plug it in. T of n equals 4 n over 4 plus O of 1. You can check the values. It's gonna be probably, if I remember correctly, it's gonna be the last one. Because A is 4 and it's bigger than B, which is also 4, but D is 0, so power 0, that's 1. 4 is bigger than 1, you get the last one. So it's of complexity n of n log base 4 of 4, and this is just 1. So the whole thing is just O of n. And it kind of makes sense because you're only doing O of 1. So each one of these, okay, it gets broken down into 4. And then each one of these 4s, again, it gets broken down into 4 quarters. But each time, these guys are only doing O of 1, O of 1, O of 1. So when you sum up all the O of 1s, it's gonna be roughly n O of 1s, which is O of n. If it's confusing, I don't blame you. But it'll be more clear. Like the assignment is gonna, you have roughly the same idea that you have here. If we go all the way, okay, is it fine? It's searching through every list, no? So it's fine to assume we wouldn't care about the C power n. I don't understand what you mean we don't care. Is it searching through every list? Sort of, yeah. It's searching through all the lists to get the max and min. But what do you mean we don't care about the C power Cn power d part? Regarding big of O, still not sure what I get, because we wrote O of 1 instead of whatever the number times that we search for. Mm. No idea what you mean. Can you repeat it one more time? While you do that, if we go back to this first question, where we were trying to recursively get the number of digits, this complexity, it's like T of n, such that n is the number of digits in your number. This n is different than that n. Assume here, no, it's just the number of digits. So how is it getting related? It's going to be T of n minus 1 plus O of 1. Like the testing for the F cases and the modulo and that stuff. So this, for example, is another relation. This is also going to be O of n. Because, okay, T of n is going to be T of n minus 1 plus O of 1, which is T of n minus 2 plus O of 1 plus O of 1. And it keeps breaking down till it's like n times O of 1, which is O of n. Okay, so different example, but sort of the same complexity. It's because d is 0. Like in these in the function that they gave us, you have t of n, your original, it gets broken down into 4, but the rest of the complexity, like what is T of n doing besides breaking down into 4 sub-recursive calls? What is it doing? It's doing an if statement. It's doing the function, but on a constant amount of elements in an array. Yeah, the searching of every list is here in the recursive call. The rest is just O of 1, like you're doing just a bunch if statements or calling the function for a constant amount. That's just O of 1. Okay, great. Last question, and we're done for just the functions. We're not even talking about counting yet. So, last question. If you still have the energy, I appreciate it. A vending machine dispenses books of stamps, accepts only $1 coins, $1 bills, and $5 bills. So you have some machine, it's only gonna take $1 coins, $1 bills, or $5 bills. Find a recurrence relation of the number of ways to deposit n dollars in the vending machine, where the order in which the coins and bills are deposited matters. So we want to find a relation such that like the order in which you put the dollars, it matters. So let's say AN is the number of ways you can put the dollars, and N is the number of dollars. So A100 would be all the possible ways you can enter $100 into this machine. Remember, it only accepts this, and the order matters. So A100 is what are all the sort of ways you can put. For example, you can put 100 coins, or you can put 100 this, or you can put 50 of this, 50 of this, and all the possible permutations, and so on. So what's the relation of AN with the rest? So, any idea? Like if I use, for example, I have n dollars, right? It's possible that I use one coin. So AN would be 1 times AN minus 1. If we're assuming here I'm only using the dollar coin. If I use a dollar coin, the number of ways that's left is 1 times the rest of my dollars. What about if you consider the bill and the $5 bill? Take a minute on that. So this is similar to the question about upright, right? Before, we could only go up or right if we are allowed. So maybe this is better, either up or right if we're allowed. Here, we're saying, okay, I have n dollars. I can either put a coin, and then that's n minus $1 left, or I can put a dollar bill, that's n minus $1 left, or I can put a $5 bill, that's n minus $5 left. So this is the counting, okay, or this is like the possibilities. How many ways do I have? Well, from here, I can either go like this, or like this, or like this. Then this one breaks down itself. If you use another coin, that's n minus 2. Another dollar, n minus 2. A $5 bill, n minus 6, and so on. So an is gonna be an minus 1. This is if you use this thing. Or an minus 1 if you use this thing. Or an minus 5 if you use the $5 bill. So an equals 2 times an minus 1 plus an minus 5. Just reimagine the whole upright scenario. But here, instead of upright, either dollar coin or this thing or this thing. Okay? So that's part A. That's our relation. The number of ways I can put in $100, it's the number of ways that follow putting a coin or a buck or $5. Well, what are my initial conditions? Well, n has to definitely be greater than or equal to 5, right? This relation would only work if n is greater than or equal to 5. I can't use this if I only have $3. So by initial conditions, we have to figure out A0, A1, A2, A4. Because after that, A5, I can use my relation. So A0, A0, where are you, my pen? A0, you have $0. So what are all the possible ways to put in those $0 in your machine? You just don't put anything. There's only one way. You don't put anything. That's it. What about A1? You have $1. What's the possible ways to put it? 2. You either put the dollar bill or you put the dollar coin. A2. Remember, this is the number of dollars you have, and this is the number of ways you can put it. A2, you have $2, so it's gonna be 4. Why? Think about it. You have $2. So coin, coin, dollar, dollar, coin, dollar, dollar, coin. Kind of like 2 times 2. A3 is going to be 2 times 2 times 2, which is 8. A4 is going to be 16. So those are all your possible, or sorry, all your initial conditions, such that this relation. Okay. Finally, how many ways are there to deposit $10? So $10, how many ways can you deposit them? Oh. Well, we have my initial conditions, I have my relation, I just have to plug it in. Okay, so what do I want to get? I want this. I want A10. But in order to get A10, it's going to be 2 times 10 minus 1 plus 10 minus 5. But I don't have these values. I don't have them. So I need to wait for them. Kind of like a recursive call. Now A9 It depends on this and this. Okay, I know what A4 is. It's 16. But I don't know A8. So you keep going. Now you try to get 8, but it depends on 7. You get 7, it depends on 6, until finally you get 6, depends on 5. 5 depends on 4. You know what 4 is, you know what 0 is. 16 and 1. So 2 times 16 plus 1. Okay, now you know A5 and A1. You calculate that, and you keep going. So that's how you get A10. And that's almost very similar to what we were doing with recursion. I wanted to get this value. But in order to get it, I need this. So the recursive relation, A10. In order to get it, you had to calculate first A9 and A5. But in order to calculate A9, you had to calculate A7 and, sorry, A8 and A4, and so on. Keeps breaking down. The answer for this is the sum of these guys, and keeps going back all the way. This is almost what would actually happen. Okay, any questions? Like, we're done, what's left is counting. We'll see how we can do that. So, almost as recursion. What's the time complexity of this? Good question. So the relation is T of n equals 2 T of n minus 1 plus T of n minus 5, or literally what we were writing with A5 to AN minus 1, AN minus 5. So it doesn't really, I think, fit with Master's theorem. So we're going to have to actually analyze it so we can figure it out. At the moment, I'm not sure. It looks like merge sort, kind of looks like it. I want to actually mention one last idea about this. It's almost as recursion. Why do I keep saying it's almost? Because I calculated A5 here, but that doesn't mean it's the same A5 here. So bear with me, last minute and we're done. You have A10 breaks down to A9, A5, right? You need both of these values. What does A9 depend on? 8 and 8 depends on 7, 3. 7 depends on 6, 2. And finally, 6 depends on 5 and 1. This is how it would actually, if this was recursion, this is how would it actually happen. To calculate A10, you calculate A9 first, and then you'd calculate A5. But to calculate A9, you need this and this, this and this. At the very bottom, you calculate A5, which is A4 plus A0. Go all the way back up, you get the answer for A9. But now on the right-hand side, you have to do the same calculation for A5. Like it doesn't, like if you got the answer for A5 here, doesn't mean it's the same, that you can just use it here. So this is, the problem with this is we're doing multiple calculations for the same value. Like imagine we were doing it for A11. Well, A11 is just A10 and A6. So you'd have to calculate A6 again, even though you already calculated it here. Plus now we're calculating A5 3 times. So it's probably more than merge sort. Or maybe it's the same, not sure. But what I'm trying to hint here is something that's called dynamic programming. If you're gonna be going to programming either in your major or whatever, This is going to be very helpful because this solves our problem. Like right now, A5, I calculated it 3 times. This solves it. And imagine, if you can imagine if I'm doing A20, how many times I'd have to calculate A5 or A6, A7, and so on. So what does dynamic programming say? Imagine you have, or what it says is you don't need to calculate the values more than once. You can figure out a clever way to do that. Exactly, it is the same value, A5 here and here and here. It's the same value, but you calculate it every time you have to calculate it. Like you're not saving it anywhere. So dynamic programming, one of the ways is to save that value somewhere. So imagine you have a list of size depending on what you want to get. So let's say it's a 11. Starts from 0 all the way to 11. Once you calculate, for example, A5, which is here. Here A5 gets calculated for the first time. Once you do that, put it here. So something like, what was its value? Its value is 33. So you put 33 here. When you reach this part, before you actually go and calculate A5, you check if you already did. If you already calculated A5, you just use its value. And the same thing for any other A. So you have a list of size 11. Before you do the recursion, before you try to calculate its value, you check if you already have done that before. Like that's one of the ideas for dynamic programming, which is very important, but it's not required from you at all. Like I assume you might get this you might start using this in your senior year. But it's nice to have an idea about that. Okay. I'll leave you with this. If you have any questions, let me know. I'll leave you with this. Try to make a program reusing what we save in the memory. Exactly. If you calculated something, save it in your memory so you use it before. Don't let it just fade away in the air like we did with A5. So I'll leave you with this. You can try to solve it. Write a program, just a normal program, doesn't have to be recursion, that calculates n factorial. And think of way if you can use this list to dynamically program it. Like assume I'll tell you n factorial maximum, it's going to be 1 million. Can you use that information to dynamically program it or whatever? Okay. Oh, you don't have to worry about it. I thought again, it's not required of you, but it's if you found it interesting, you could try to do that. Okay. If you have any other questions, let me know. Otherwise, good work on making it this far with me. Anytime. Anytime. That's great to hear. Yeah. See you next time.